Hey everyone. So today I'm going to be doing a dynamic programming interview. So I have my friend Alpha again, who's going to be testing me, going to ask me a few DP questions. You want to quickly talk about how you're going to format this interview?
Yeah, so I the easiest way for me is I'm just looking at the neat code like 150 or 250. And we're gonna
Okay,
start with some easy ones, and then depending on how you do, I'll kind of see which ones to ask you next. So
nice.
we'll do 2 or 3 questions kind of depending on how you're doing.
Yeah,
And then the difficulty will kind of depend on how you're doing as well.
cool. Sounds good. Yeah. Yeah, let's just start from basics because I haven't done a DP question in a while.
Okay,
So
okay.
yeah, if I easily do it, then yeah, ramp it.
Mhm. So let's do this one first. This is like the standard easy one. And yeah, I'll let you take it from here.
Okay, sounds good. So let me all right. So we're climbing a staircase and it takes n steps to reach the top. Each time you can either take one or two steps. Pretty much in how many distinct ways can you climb to the top? So let's see this. Okay, so we have example one here, and then we have example two. So we have the first one, which is two. So how can we get to two? We can either get there. There are two ways to climb to the top. You can either take like one step plus one step, or you could just straight jump to it. Try to visualize this, fix it.
You can
Or
draw it in the
yeah, let me
drawing if
draw.
you
All
want as
right, all
well.
right. Yep, one stuff here.
Okay, get rid of that.
So let's do. I mean, n equals two. So pretend we have two steps. Two. We want to get to. We want to see how many ways we can get to the second step. So if we start here, we could just jump right away, or we could
Mhm,
like jump here and then jump here. That's why it's equal
mhm,
to two. Pretend we wanted to get three. Pretend we wanted to get three. We could have jumped we could have jumped from here, or we could have jumped from here, right?
mhm.
So I guess what we could like all we really need to know is if we're looking at a specific step, we just need to know. I mean, we could have got there from this step, or we could have got there from this step. Well, we kind of just if we knew, we could kind of do it top down where like if we knew how many steps it can get from here, and we also knew how many steps it possible ways it could get to this step. If we just add those up, then we know how many steps we have here. And we could kind of do that top down. Like we can look at it going backwards a bit. We can go like top down or bottom up. But let's see. Because how many times can we get to this third step? We can either come out from here or come from here. And then we could just ask the same question for this guy. This is I'm thinking for the top down. It's kind of like, oh, we could have came from here. And we don't know how much times, or we don't know how many steps. Like we'll have some base case here.
Mhm.
This will take zero steps. And then from here, then we could have came from here, or we could have came like to two steps. So we could kind of ask that question, and then we can like recursively go down. But then, for example, if we already calculated, because this will recursively go down, if we already calculated how many steps this we already calculated how many steps it takes to get here. When we ask that question for this guy, because this guy's gonna ask it for here and here,
Mhm.
we don't need to recursively go down. Because pretend this is long. If we already calculated for the first guy, we only need to do that for the second guy, essentially. Or we don't need if we already did it for the first recursive call, we don't need to do that same work twice. If that makes sense. So
Yep,
we can
makes
quarter
sense.
cache that. That would be like a top down approach. But then
Yeah.
That would be, I would think, that would be around the O of n type complexity, because for each of the steps, we calculate it once.
Yeah, I'd say for when you're learning DP, I would just start with top down. Even there's like some slight optimizations you can make with bottom up, but I would just completely ignore bottom up. Be
Okay,
able to do 90% of questions top down, and then you can look into bottom up if you want to.
okay, sounds good.
Unless there are rare cases where it's more intuitive bottom up, then I would go with that if it's more intuitive to you bottom up, but
Yeah,
it's very rare. So
yeah, yeah. That's kind of a. Let's see, how much time was that? I was like, I was trying to. I was still trying to limit out for 20 minutes, so I kind of gave a terrible or try to solve the question really fast. So it's kind of a bad explanation. But let me implement the code and yeah, maybe give you feedback on how I can explain that better.
sure.
Let's see. So I think let me write out the function here. So
Mhm.
what we're gonna do is we're gonna try to see how we're gonna try to climb the stairs. So we're gonna say let's just create a simple function called num stairs, and I'll break it out into others if it needs to be. Because we could do like a delete code switch.
Yeah, we don't need that. We don't need delete code. You can just make it.
Okay, let's just do this in case we need to manage some state.
Okay,
But
sure.
what we're gonna be given an n, right? So what is the n? What would do we need to do here? Let me load up this whiteboard. Basically, what it's gonna do is we need to handle base cases. So if n is equal to, we need to handle a base case. So if n is equal to 0, is there constraints? So I forgot to clarify as well. Is there constraints on n here? Could it be negative number? Can it be 0 or 1?
So we'll just say it will always be positive. It'll be at least like we'll just keep it simple. We'll just say it's two or more.
2 or more?
Yeah.
Okay. If it's 2 or more. Okay. If n is equal to 1, then we'll just return 1. Right? There's only one way we can get to 1. N is equal to 2. What is 2 here? Then return 2. These are our base cases. Because there's two ways to get to 2. You can either just jump straight to it or jump, like take 1 and then 1, right?
Sure.
So we handle our base case here. So now we're handling all these are anything n is greater than 2. And basically what we can just return is um self downstairs of um like we can get there from taking n minus 1, which is plus n minus 2. Like I mentioned, we just need to add up how many times we can get from the stair behind us, just one step, plus the amount of stairs we can get, like if we jump from the second stair, like two stairs behind us. And this would be
Mhm.
the brute force because we're recalculating sub problems here. Like what if I call it with n3 multiple times? So what I do, what I'd want to do is cache that. So I would just build like a simple recurse function. So and cache, put this in here. And what I do is like I'll cache the result for n and then just return that value kind of thing.
Okay.
Now and then what I do here is I'll basically just return self dot recurse. I'll pass n and I'll just pass in like an empty dictionary, and that's how I would cache the result. and then now I just need to save that. So, or I actually need to use that cache. So if n is in cache, return cache. cache.
Okay.
So that will memorize it. I think that will get the result. Should I dry
Yeah, I
run it or
think so. Yeah, we could do a dry run.
okay?
Yeah, I haven't seen anyone write it this way before, but it makes sense to me.
Let's do yeah. Let's do 3 real quick.
Mhm.
This is kind of how I do my DP problems. That's why I suck.
No, it's totally
So
fine. For one thing, people usually start at like 0 and n, not backwards, and for another, they usually don't make, I mean, I think this is better, but they usually just put helper in their original one. But this is fine too.
well, they start at 0 here?
Uh, I mean, they start at well, what I'm saying is, like, in here, they usually just like a DP function and then call it, so it would all just be in one, then they make a cache. This is fine, yeah.
Okay. Let's see.
Yeah, I mean, either one works, yeah.
Let's just start with n equals 3. And I guess we could like open this up like a recursion tree. N equals
Mhm,
3. So what is n equals 3? Since it's not equal to 1, it's not equal to 2, or it's not in cache. We
mhm,
could have our cache right here. Since it's not in there at all, we call n minus 1. So we actually call like n2 here,
mhm,
right? And since n is equal to 2, we just return 2 there. So this guy kind of like gets 2 right here. He's gonna add another number.
mhm,
Then we call n minus 2. So we basically get n minus 1 here.
mhm,
N minus 1 is equal to 1. We get like 1 here.
mhm,
And then now we store that in the cache. Equal
mhm.
to 3, right? But that we're calling this for like n4. So this will call n3 here. This will call n3 here. So
Mhm,
what's n4? N4, this will return 3, and then it'll return plus. And since 3 is already in the cache, when it calls, wait, minus 1, minus 2,
Yeah, I think that
minus
needs to be
2.
on 2.
Since
Yeah.
this is 2,
Mhm,
2 is already in here, so I'll just return 2. It's 5,
mhm.
5. And we store that here. And like we could keep like going on that. But essentially, like if we do like n5 here, it would be kind of the same thing where pretend it might get more interesting. This will get more interesting after n5, I guess.
I mean, I think I get what you're I think you have the understanding down fairly well, so I think we can,
Okay.
yeah, maybe stop at this one.
So yeah,
Right.
this will just return 3 and then get
Mhm.
5, and 5 plus 3 is 8.
Okay, so let's try running it on these, and then let's try a bigger number just to make sure we're getting the right thing,
Sure.
and then we can but yeah, this was
Do
pretty good, and you understood the cases very well, so
let's do 8, 5.
sure.
Um, let's print. Or like if I was really try harding into sorry.
Okay. Well, do you know what it needs to equal?
I think
Okay, it needs to,
8
I just ran on LeetCode, it's 8, yeah, so, okay.
ran. What if this was 7? To this here.
I got an error. Oh, because you
Yeah,
changed it.
change it.
So, like,
It runs if I do 8.
Mhm.
Yeah, it was a classic DP one, but how was the
Wait,
explanation?
did did it say successful or am I not seeing it?
It should say success. Okay. Well, it doesn't even run the second line. It would if
Oh,
I move this,
I see.
it
So
just breaks.
it doesn't show the result. Well, it just throws an error if it didn't. I
Mhm.
see. Okay, yeah. Okay, yeah, no, that was good. Yeah, so the main things I'd point out, so once you recognize all DP is, it's literally just state, a base case, a cache case, and a recursive case. Every problem just follows the same format. So that's all you got to think about. It's like, okay, what's my base case? How do I recurse to get down to it? And then, yeah, just storing in the cache. And the other thing is, especially for 2D DP, you need to figure out like what's your time complexity quickly. So typically the time complexity is just going to be all your state multiplied by each other. So state one times state two, whatever. So you want to think about like, okay, how big can these be? And then roughly what's that? Does that make sense? You have more states?
Yeah.
Okay. And then your space is usually also a state. And then you want to think about, okay, is my recursive thing in O1 or O then? So in this case, it's O1. So like that's why your time complexity is O then because you have n state, you have a O1 recursion. So you have O1. If you had like a loop in here that went like 0 to n, then it would be like n squared. So once you can
Okay.
quickly figure out like what's my complexity, the rest of this is literally just all boilerplate. You just change a few lines.
Okay.
Does that make sense?
Yeah, that makes sense. Yeah, let's get into a harder one then.
Okay, yeah. So let's do a harder one. So I feel like house robber is kind of like the same thing. So let's get into another one, and we'll do this one. Yeah, I think this one. Yeah, we'll see how this goes. Or actually, let's just do instead of that one. Let's do this
I'll delete this for now.
one. Copy it. Okay. Yeah. So this is another like really common one. Oops.
Okay. Can you read it over? You're given an array of coins representing coins of denominations 1, 5, etc., and an integer amount representing a target amount of money. Return the fewest number of coins that you need to make up the exact amount. If it is impossible to make up the amount, return -1. See.
Mm-hmm.
So, um, let me go back this a little bit. Okay, we're given the different denominations, right? We're given like okay, we have a $1 bill, $5 bill, $10 bill, and we
Mm-hmm.
want to figure out what is the minimum number we can do. We can get to 12 to. I think the reason why we need to use DP is because we can't like greedily choose the biggest coin because
Mm-hmm.
that might affect our decision down the road. Let's try to come up with a better case. Pretend it was like, what's a case when um we can try to craft a case. I think if I was try like the thing is we already mentioned this DP, but I think the hard part was figuring out if it's DP also.
Mm-hmm.
So the way I would do that is try to find a case where greedily choosing, because what I'm thinking here is like if we just keep choosing the largest denomination, what if we can greedily choose the largest denomination and actually get the result? Why do we need to use DP there? That's the thing I would be questioning. So
Right. So can you think of a counter example for what you said? And
yeah,
then that would be.
let's try like 13.
Mhm.
My biggest number was like 9. We had 9. We have like two, two. Oh wait, like we have twos. So it would take 3 to get here,
Mhm.
or like pretend it's just 12. We have 9 and 2,
Mhm.
and then we had like instead. Or let me craft the case. This is interesting.
Yeah, so just here, so just this, if you add one more number or it's the yeah, like Like add like a 6 or even this. Yeah, this is
Well, yeah, let's add a 6. Let's add a 6. We add a 6, we can get there with 2. But here, but if we took 9, then we took 11, then we took 1, that would take 3. So we can't just like really choose that number.
also the really easy example is what if we have like we get rid of the 1, now we pick 11, but then we can't solve it. So
That's true.
that's the other thing. Like the biggest one might not always solve it, and then yeah.
That's
And
true.
then
Yeah. Okay. So I think that's how I kind of identify its DP.
mhm,
Um, if it since it is DP, then um, like you mentioned, let's just work through a top down approach.
mhm.
So let's see. I
Yeah, so
mean,
can you kind of like those things that I said? So you need the 3 things, like the state, the base case, the recursive case, and then
yeah,
estimated time complexity. And then from there you can just code.
I think like when we call this function right on 12,
Mhm,
what do we need? We need what are the different base cases that we need to do? I think it's kind of similar to the last DP question where we have different denominations, right? We have go with this case. Or let's go with this case, right? 12. Pretend these are denominations.
mhm.
I mean, we like pretend how could we have got to this 12 coin? We could have got by taking one. So that means this would have been a like F11.
Mhm,
Because we could have took one coin to get there. Or we could have took F7, right? That means that we jumped to this from 5. Like if we take 5 as a denomination, then we just need to figure out like if we take the coin 5, we just need to figure out what's the minimum amount here that what's the minimum amount that we could get the target of 7. And then the same thing here with 10. We just do like F2, right? We kind of recursively do that top down from 12 and try to cache on this number. Basically what we're going to cache is like F at like an N, and it's
mhm.
like the minimum the min of like the different denominations I could have took to get there, right? Because we don't know which one, so we should try the different ones. We should try two, and some might not actually, like you mentioned, some we might actually not lead us to actually get to the right result. So we need to be able to capture the fact that like we took a denomination that didn't work. But essentially, what we're gonna try to do is we want to choose the denomination that will minimize, like the children that we call is minimized, or the value that we get back after recursing is minimized. Does that make sense?
Yeah, yeah. So what would be our base case here? Or yeah,
I think the base case would just be the different denominations. Let me see.
well, I mean, how do we know when we can stop recursing? Is like your climbing stairs thing. You said
Yeah.
like when you're at this thing, return this thing. It has to be like the denominations are what you're caching.
Mm.
But or sorry, what do you mean
Or
denominations? Like if I'm at if I'm at one of
sorry.
these, that's the base case.
Yeah, I guess the base case is essentially base case is like we need to get to 0 because we need to
Right.
get the total exact amount. So like
Hmm.
if F could actually get to 0, um just just like that's the base case. But if it gets under 0, that's an error.
Right. So we want to make sure that well, we can't like throw an error. But I guess if we want to think about what we return for these, so these are kind of like the two things where we want to stop, right? Either we get to 0 or under 0. And
Yeah.
we're trying to minimize the number of coins we're using. So what does it make sense to return for each of these? How do we ensure we never take this thing
Yeah.
as our solution?
I guess like when we're looping over the denominations, we just don't loop or we don't recurse if it's gonna get it under 0. But
That's fine. Yeah, sure.
and then what we'll do is we'll yeah, the base case, I mean, if it gets to 0, we just take 0 coins there.
Hmm. Yep.
I think that works. And if when we take specific coins, we just kind of add 1 plus like the function call. Because we're taking a coin, but we need to add 1 to that function call.
Yeah, yeah. Yeah, I think
Okay.
you got most of it.
Let me try implementing it.
Mhm.
S-
Yeah, it is also funny you're writing the LeetCode code format because, like, if you ask us about an interview and you write, like, class solution with, like, the LeetCode stuff that we can.
Yeah. I like to do it this way because I like to do the helper function. So
Yeah,
let
I think
me
that's also, like, cleaner Python syntax as opposed to just writing helpers in the function. So
def first. So us. So what we're gonna do is what are we're gonna be given an n again. We're gonna say return self. I mean, there's gonna
so we're given a coins array and an amount.
oh yeah, um, coins, and we're given an amount. Self dot recurse, and we're gonna be given the coins, the n, and like we know we're gonna be caching, so just gonna throw that in so we save time. So what we're gonna do is yeah, let's talk about the base case. If the n is actually equal to 0, then
Mhm.
we return 0.
Okay.
Like if we probably don't want to recurse if it's less than 0. But what we're gonna want to do is we're gonna have to keep track of a minimum value. So let's do float infinity. And then eventually we're gonna want to return that min val.
Mhm.
I think here we'll like if this actually equals float negative infinity. I mean, what do we want to do if it can't? Okay, we want to return -1 if it can't be made of those coins. So if
Yeah.
we recurse on that and it returns negative infinity, let's return -1 or let's go this result.
Yeah, I'd definitely save it this year.
Yeah, not to call it twice, right?
Well, yeah, I mean, it's gonna be cat. Well, yeah, you'll send the new cache, you will call it.
So if the result equals flow negative infinity, return that otherwise. Okay. That just handles that case. So what are we gonna do? We're gonna loop through the different coins and we're going to try to figure out the values here. So for coin in coins, if n minus coin is less than 0, then we just continue. We don't want to deal with that case. Right? So we don't want to recurse there.
Mhm.
Otherwise, um, sub result. This is the result of the sub problem. We'll actually recurse now.
Okay.
And we don't need to really like we could just take the same coins over because it's not like it's like if they use the coin like they you can use coin one multiple times.
Mhm. Yeah.
So let's just pass in the coins again. And then let's pass in n minus the coin now. And then
Mhm.
we'll pass in the cash. We'll say min val equals the minimum of the min value here. I mean, okay, and then we're saying since we're taking the coin, we're adding here. So this signifies that we're taking a coin.
Okay.
So each of the subproblems is going to add one to them. But with the min val here, um, yeah, at the end, we want to also add the cash. So same thing here. We do cash n is equal to cash of n is equal to the minimum val.
Mhm.
And then like if n is in the cache, then we return just the n cache here as well.
Other way.
And then, oh, sorry, you're right. If n is cache, then yeah, we take the cache and then we return n there. So we don't recalculate that.
Mhm.
I think that should work. I don't know if you want to, should I dry run it?
Sure. Yeah.
Okay. It's like, let me send out a message to someone. That one.
Okay.
How does that look so far?
Oh, looks pretty good. Yeah, no, I think you're getting this very quickly. And like I said, if you top down, it's really easy. It's all the same stuff. So yeah, once you recognize it's literally just it's gonna get harder once there's more than one state. And they're not so easy to find. And like you said, you have to recognize DP. That's also
Yeah.
not the easy part. But
Let's do a
yeah,
harder one then, because I think this one might work if we just copy and paste it. I don't know.
yeah. I mean, you have a small error. I think it's just everything else
Oh
looks
yeah,
good.
right.
Some slight things you can improve on is you can actually sort the array,
I
and
see.
then instead of continue here, you just break. Because
I
then,
see.
like, if this is too small, then all the next ones will be too small or whatever. But that's like some small stuff. Also, you can make so you were trying to avoid getting negative numbers. You can also make that a base case. You can just say, if n is less than zero, just return infinity, and then that will
I see.
automatically like never use your thing.
I see. That makes sense. Yeah.
But you can do it your way too, either one. Yeah. Okay. So let's look at.
Yeah. Just slightly harder.
Yeah, I'm trying to find the 2D one that's like not too hard.
Once you realize it's DP, it makes it easier for sure, but that's
Mhm.
kind of the hard part.
Okay, maybe we'll go with this one since it's not so bad. Yeah, definitely. Well, so I like to think of GP as basically like a brute force with a cache. So like you can't think of, and also the other thing that you can kind of look for GP is whenever you have non-continuous chunks of items. So if it's continuous, you basically just always want to use like sliding window or 2 point or whatever.
Mm,
But when it's like I can pick what things I can take and what things I can't, and like I can skip over, then GP is basically just like a brute force with a cache so that you can quickly figure out, okay, what's the type of complexity here, and does this work? And then you can write that out, and then there might be something better, but that's like the default for anything that is like not continuous. That makes sense.
yeah, that makes sense.
Yeah. So it's really common. Yeah, for decode, I guess. And yeah.
Okay. Take a look at this last one.
And then yeah, maybe we can do some like harder ones in a couple weeks or something to
Yeah.
do more
Need to treat.
that aren't that.
I definitely I'm realizing I had the basics. That one yesterday was just a straight hard one, so it's hard, like the. I mean,
Yeah, I think that one is definitely tougher than these. But you were saying like I don't even know if I could do DPA. I have the basics down pretty well. You can draw the tree. You understand like the reason for caching. So we can definitely like ramp it up in a few weeks.
nice. Yeah. Yeah, I think I could solve that other one if I build up towards it. But it's like I haven't wrote a DP question in a while. So
Well,
just
most
trying to.
people who haven't done DP will even do that climbing stairs and will just get stuck.
Okay.
So yeah, you're definitely not there.
Okay, so we're given two strings, text one and text two. Return the length of their longest common subsequence. If there is no common subsequence, return zero. Okay. A subsequence of a string is a new string generated from the original string with some characters deleted, but you don't change the relative order. So let's look at this. For example, ACE is a subsequence of. I see. A common subsequence of two strings is a subsequence that is common in both strings. So let's just look at the example. Not 100% understanding it, but if I read through the examples, I think it'll make some sense. So we have A here, A here. Okay, the longest common subsequence is ACE because yeah, you can delete elements from either of these without and maintain the same order and still get like ACE. Or yeah, and you can build ACE. What are some other common subs? Let me look at some other common subsequences that might be shorter. Like B would not be one. C and E would be one. Like CE would be one, but it's two.
Mhm.
And just straight E would be one. But like E would be
Yep.
one as well. Right. So we're just trying to find the maximum one.
Mhm.
Then what I would think at first, what I'd be thinking is like, how would how would we know if it's greedy or not?
Mhm.
Let me think that.
Or what would greedy even be, right?
Like, one greedy approach maybe would be, what if we just like, okay, A matches, so what if we choose that one, right? Like, for this one, it works that we choose A.
Okay, A matches and then the next letters don't match. What do you do?
Like, what if like it's like D D D, um, like you like picking A there wouldn't be optimal. That's what I'm thinking. Or pretend it was like this, A.
I'm not seeing you writing. Let me
Oh,
restart it. I'm just gonna refresh it.
do you see it
Okay,
now?
okay. Yeah.
So I'm thinking here is like, a greedy way would be like, okay, we just match A and then we match it here. Like the what we're making decisions, right? Like we can choose A, but then if we choose A, we're not we'll have to match it with A and we miss out on all of these ones. Right? Like how do we know we don't need to
Oh, I
include
see
A in
what
the
you're saying.
result?
So you're saying like, do I have to look for this letter or not? I
Yeah.
see. So you're basically okay.
Like
Yeah.
the optimal here is like picking D or something, or picking D here and then matching it with D's D and not actually like A.
Mhm.
But if we put A up front, then we'd actually need to pick A. So that's why it leads to like you can't really just do greedy because how do you know that we can or can not choose A without, because it affects your future decisions. Because if
Okay. Now let me ask you. So in your example, when the characters are the same, like the characters at a certain index are the same, is there ever going to be a case where you don't want to take that,
if,
or do you just always take it?
if the letters are the same,
Yeah, like if first two letters are the same, let's say, would you just always say that's part of the match, or is there a case you could think of where you?
if the first two letters, I would always take it because it's not going to really affect anything.
Yeah,
It'll
exactly.
just
So
always increase
yeah,
by one. But if
yeah,
this
yeah,
wasn't the same and it was somewhere down here,
mm,
I would have to think twice because I'm already missing out on a bunch of characters that
yeah,
I could match with eventually.
yeah. Okay.
So what I'm thinking is a good one. I think I'm trying to see how we could do this top down.
Mhm.
I think the inputs to the function are going to be two substrings
Two substrings, sure.
or two strings in general.
Two
Two
strings, yeah.
strings could be like, would be something like this.
Okay. And then can we think of those things I was mentioning, like the base case, the recursive case, and yeah, I guess you already mentioned the inputs.
Like this, these are the inputs for sure. I think I'm trying to think of the base case. The base case would probably be if we have empty strings, if we get down to the empty string.
Yeah. What if one's empty and one's not?
Yeah, that would also be a base case, but it'd be that it would be like an invalid case. Or what do we
Why would it be
return?
invalid?
Because you
Like
can't.
like if
Oh,
I
this would be
I have
zero. Yeah, this would be zero still.
yeah, so if one of them is
Yeah,
empty
if one
or
of them
both,
is
it should be zero. Yeah.
base case is one of see.
And then kind of like what are the choices we can make?
Yeah. I guess what I mentioned was that I mean we could choose the element or we could not choose it.
Okay.
If we choose or we can choose to include this into the result or not.
Mhm.
Pretend it's this case. If we choose to include this into the result, then we could skip all of these guys and just pass down into the child. Maybe okay, but we already used A, so we'll just pass into child C. Like we'll have to pass in this guy. So we'll basically call it with like F. We'll call it. We'll remove that element, but we'll also for like when we call the child, we have to call it like this because we can't use all these ones, and we used a, so we can sort of store it like this.
Okay,
We'll
so
call it here.
with this approach, whenever you pick a character on the left, you're basically saying, if I include it, I have to loop through the right, I have to figure out where it is, and then I have to get like a substring. So that's like O then. Is
Yes.
there any other decision we can make that's faster?
Like we could just maintain indices there.
Yeah, we can maintain indices, yeah, instead of making substrings, but regardless, if we choose to pick this letter A, then we need to figure out like, okay, where is it approach in our next substring? And it could be at the very end. Um, so still gonna take a while. So is there like, can we have a recursive process that's not like, can we take this letter from the left and find it in the right? Can we do something else?
Yeah, I guess we could just simplify where we could just like fast down this, right? Put one less down.
Yeah, exactly.
This,
So we can just say like, well, we're just gonna move one of these strings up one.
there's
Like it could be one, it could be the other, right? So if we take the A, like or maybe we'll take the A, but if we choose to like go down one of them, we'll pass down the next one. And we could have the other approach, right, where we take the first string and we move that down a character. Or we just say like we don't want the A. Does that
yeah,
make sense?
yeah. So okay, yeah, that makes sense. So we have the base case and our recursive case, we take one
Mhm.
or don't take it. If I take one, we essentially need to, well, it needs to, in order to take one, it kind of needs to equal.
Yeah. Well, yeah. So I guess there's two cases, right? So what happens if the first characters are equal? You already kind of mentioned this ahead of time. So when I
Yeah.
asked you, right? Like
If
they're the same.
yeah, if it's equal, we just increment both pointers, but we need to add one because that means
Mhm.
that we can get a subsequence of one at least.
Yeah, yeah. And if they're not equal, then what are the choices we have?
I guess if it's one, we could just increment, and then there's no cases really. But if it's not, then we need to take the minimum or the maximum of like either moving this guy up
Mhm.
or or moving or moving this guy up or the other one. But like we either move this pointer up on this on the first string or the
Mhm.
first pointer up on the second string or the second pointer up on the second string.
Yeah,
Or
exactly. And so we're not committing to taking something, but this is like we're shrinking the string and we don't have to like search for where does this appear.
that's yeah, that makes
And
sense.
then we can also use pointers instead of substrings so we don't have to like, because I think, yeah, you mentioned this before in some of your interviews, right? Like if I take a character off of a substring at every iteration and make a new substring, that's low event as well, which is not good.
Yeah,
It's
that
very
would be
consistent.
make it super inefficient. I think
Mhm.
yeah. So we call it if we increase commit one pointer, and then we could just work with pointers here,
Yeah, exactly.
and we can cache based on pointers, not strings. Because also those comparisons, if we're using pointers, will be faster.
Yeah, like if we have like a huge string, like in a cache, that would be not as good as just like an index, right?
Yeah. Let me try implement that out real quick.
Mhm.
You do this too in the interview or no? Like build a class.
Uh, I never got asked DP in any
I've
interview.
never been asked DP in my life in interviews. Crazy.
If I get asked this kind of stuff, though, yeah, I don't know. I mean, I could go this like 5 minutes. So I'd have to think about
Yeah.
it. Right? How do I like pretend? How to-
Um. There's your text one, text two. Let's say pointer one,
Okay.
pointer two. So we have these, and then we're gonna be storing a cache.
Mhm.
So the same thing is our base case, right? If text one, the length text one equals zero, or the length text two is equal to zero, we just return zero, right? Because there's just like there's nothing we could do here.
Yeah.
That's the base case. Zero as in the longest common subsequence is zero.
Mhm.
And then now let's work through our case. But like if text 1 0, or sorry, no, we're working with pointers. So we pass in the pointers here. If these are actually equal to each other, then we could just return, but definitely store something in the cache here. Else pass. This is the other case they don't equal, but if they do, we'll say recurse self or sub result would be self dot. We're gonna call DP on the same variables, which is these ones. Mhm. We're gonna increment this one, and then we're gonna increment this one. But then we're also gonna do like 1 plus this
Yep.
result equals. Okay. What are the other results here? So this essentially means like, yeah, we're since they match, we're gonna it counts as a like A and A. So that we're gonna add 1 to the result. But then we're also gonna like do a DP there. There's only one option there really. But what's the other case? What are the two cases here that if they're not equal, we need to try left, try text one, or remove from text one. And then we could also remove from two. Mhm. And then from this, we're not actually matching anything, I guess. So we don't add one here. But what we'll do is like if we remove from one, we just increment that pointer and then maybe they'll match down the line. Or like maybe the next recursion might match. But let's do so we either move the plus one here, or we remove or we cache or we move up this one. Mhm. And then we take the sub result should equal to the max of remove from one and remove from two. We want to maximize that value. And then after, we could just return the sub result. And then we could just introduce a cache as well by doing cache. And what are we storing here? Probably a pointer of, if we get to these two pointers, then we know the result. And then we do the same thing. We just cache this as well. These are in the sub results. Return result. What happened? Um, what I just got deleted. Yeah. Does it make a sense so far? This part, yeah.
Yeah.
The pointers in cache, right. Cache, something like this. So it's like base case, cache, cursive case. And then here, now we just need to implement this. I mean, like we could just call solution here and then have default values.
Yeah, I guess that also probably works. Yeah. Never seen anyone do it this way, but it makes a lot of sense to you.
Yeah. How does that look?
So yeah, I would try running this one because you have some bugs.
Oh, really? Okay, okay. Dry running this one. Let me see. Okay, let's.
Or you could dry run it, yeah. That's fine too. I was gonna say you can just run it, but you can dry run as well.
What's the name of this question? Is this a legal question?
Yeah.
Let's see. Probably done this one before. What's the name of the question?
It's called longest common subsequence.
Oh yeah, this is classic. Wait,
Awesome. Yeah.
like, let me log in. Let me log into my lead code. Yeah, I probably did this question for sure.
Well, your bugs are kind of like they're not logic bugs. They're just kind of like silly bugs. So
Okay, wait, let me look at here.
mhm,
Let me just dry run it because in the
sure.
let's start with a simple case of we have a or we have text one equals a text two equals a.
Hmm.
Like we have pointers at 0, 0. Then we'll just build up this case. T1 equals 0, T2 equals 0. So when we call this function, if the length of text one equals 0 or we return 0, that's not the case. So we go here. The pointers are not in the cache, so we return cache. I think that's fine.
Hmm.
Then we have sub result is equal to none. So if the text one pointer is equal to the text two pointer here, okay, because we're going past it a bit. Well, okay, if the pointer we're doing like if the pointer is greater, if the pointer one is greater than or equal to, that means we're out of bounds.
Hmm.
Is that the one you're thinking?
Yeah. Yeah, because you were just checking for the length of the text.
Yeah.
You weren't actually looking at the pointers, so you would never hit a base case.
Yeah, you're right. Was length of two. So if the pointer two exceeds that, so these get incremented. Yeah,
Mhm.
no, I think that would work. I don't know. Should I run it?
Yeah, you can run it. I think. Yeah, I mean, you might have something else, but I think this is good.
Well,
And then you, I mean, from here it's just going to be like syntax errors.
it's
Your
called
logic,
longest common subsequence.
yeah, it's 1143.
Okay. Can you run it on yours?
Yeah, it's okay.
See, to log in.
It goes call something else. Yeah, long.
Let me.
I mean, I think the names are also different, so maybe you have to like change this. And you have like pointers and stuff.
Yeah.
This
You
case,
just log in on the side.
okay. Pointer one, 0. Dang. See if there's any other.
Oh, so wait, I got it up here.
Okay.
Yeah, it looks like I solved this question back in 2024. Not that long ago. But I solved it. Is it unoptimal? Interesting. Interesting. That's a good question.
So it says for A, B, C, and D, E, F. I don't know if I just called it incorrectly or what.
Well,
For
even
A, B, C, and D, E, F, it you got 3. And that expects 0. I mean, I think you did it right, so I don't know why it's giving me the wrong
it's
thing.
funny. I even named the variables the same.
Yeah, there's no way, unless I labeled it something wrong or something. I don't know. Did you try running it on your end?
Let me try it right now.
Okay. Yeah, the example 3 failed, but I think you did it right, so I don't know why.
Example three. I'll put 3 when it should have been 0.
Mm-hmm.
I get 3 there.
I have no idea, to be honest. Like, the logic's right. I mean, this is where you just throw the GPT and it's like some dumb thing. So, let's see.
Wait, why am I adding one?
Yeah, like, your all your stuff's right. It's literally just gonna be below, change the default.
Like, how is it
Potential
adding one?
side effects that from multiple calls that share the same default dictionary. Yeah, so there might be something with you having that cache, like, not sure. It might be something there, but it didn't find any logic errors, so let me run the one it suggested. Yeah, so the one it suggested is all correct. Oh, I think it said cache. Yeah, so it literally just changed like some Python syntax thing, and that was it. Um,
Yeah, maybe if I called this from a helper function.
yeah, so I don't, and it literally just said cache is none, and then when the cache is none, then it makes one, and that was the only difference, and then that worked. So it might be some like reference or something that you're like reusing or cross call or something like that. But I mean, the important thing is all the actual code is correct. So
Okay.
you just like that part. Okay.
Okay. Yeah. How's that?
Yeah, I think it was pretty solid. I think you noticed that you want to use pointers. Maybe you had a little bit of trouble figuring out that like you can't just say like I want to use a letter and then scroll through the other words. Like you want something better.
Yeah.
But once I gave you a hint, I think you figured it out pretty quickly. That was good as well. And then you found, yeah, you also figured out that when the letters are the same, you always want to take the letters. I don't think everyone comes up with that. Um, yes, I think it was pretty solid. I would just keep doing problems and then, yeah, just keep doing top down. And then, yeah, I think the next thing is going to be for you to, yeah, recognize problems are DP. And the tricky problems are the ones where the state aren't obvious. Like all of these really obvious.
Mhm. Yeah. I see. Yeah. Let's ramp it. Let's keep going. On a different one. We'll start from here and go even harder. Deeper
Yeah,
questions.
yeah.
The hard
Yeah, so
part
we
is
can do
figuring out if
this.
it's DP though. That's the thing.
Yeah, so like I said, the main things for DP is if you're taking or not taking an item, that's a big hint. And if things aren't contiguous.
Yeah.
Because DP is literally like, I'm going to go through every index and like have a decision. So I think that's the part that makes it kind of easy, I want to say, is like here, you can skip a letter or you can take a letter. So anytime you have that, it's like almost always DP.
I see.
Or like, yeah. So it's just not contiguous. And then also, like I said, if you don't know if it's DP, if you just fill out these three things, the base case, the state, and the recursive case in like pseudocode,
Yeah.
and figure out time complexity, then you can figure out like, okay, can I do this with DP?
I see.
And then yeah. And then if it's too big, then you can't. So that's the other thing is like when you create your states, sometimes they'll be too big. So like really commonly code constraints are like 10 to the fifth.
Mm,
So you can't have two states that are 10 to the fifth because that'll be too big and that will give you like field.
I see.
So yeah, things like that. And then figuring out how to take maybe some simple states they give you and make it things that will actually fit. So yeah, we'll definitely do like maybe some hard GPs or something in the next one.
Nice.
See how you do that.
Okay. All right. I'm gonna end the video here. Thanks for